This week we are learning about covalent molecules and the structures that these compounds take and how we can learn how to draw them and see them in 3 dimensions. So to start out, we need to know how to draw Lewis structures. And we've already learned how to draw Lewis dot symbols of individual elements. But once those Lewis dot symbols for the individual elements come together, they can be used to create molecules like the ones you see below. And in these molecules, these are 2-dimensional representations of how the atoms are connected to each other with their covalent bonds. Covalent bonds are shown by these lines connecting the atoms, and what electrons are not bonding with other atoms and are considered lone pairs of electrons. These are the little dots that you see next to each of the element symbols. Okay, so depending on the compound, there might only be one correct Lewis structure, but other compounds there could be multiple correct Lewis structures if they're complex enough. Okay, so let's get started with drawing these. The first step to drawing a Lewis structure when you're given the chemical formula of a compound is to draw a skeleton structure. This is like the bare bones of the molecule, and this is going to show how the atoms are connected to each other through single bonds. Okay, so there are a couple rules here. Whichever atom is the least electronegative atom is going to be the center atom, and hydrogen can never be the central atom, even though it's the least electronegative of all the elements, pretty much. Okay, so, well, of all the elements that could be in a covalent compound anyway. So, hydrogen can't be in the center, but whatever is the least electronegative should be in the center. So if we look at the first one, since all we have is nitrogen and hydrogen, of course nitrogen is going to have to go in the center because hydrogen cannot. So let's put the other 3 hydrogens around it, and we're going to have to connect them with single bonds. Okay, that's what I mean by calling it a skeleton structure. So for the next one, oxygen will go in the center because it's not hydrogen, and our 2 hydrogens will be connected to it on either side. Finally, we get to the next one, and this one is actually going to have the electronegativity more important in this problem because now we have 2 things that are different from hydrogen. Remember, on the periodic table, the electronegativity increases as you move up to the right. So, oxygen is a little further to the right on the periodic table than carbon, so that means oxygen is more electronegative. So, oxygen is more electronegative. I'm just going to say En for electronegative. And carbon is less electronegative. So carbon will have to be our center here. And we're going to have oxygen and then 2 hydrogens coming off of it. Okay. So these are our skeleton structures. Now we're going to move to the second step in drawing a Lewis structure. Alright, so it says that we need to count the number of valence electrons for all of the atoms present and sum them up, or total them out. Okay, and we'll get to that note in a second after we do that for each of our compounds. So we already have our skeleton structure drawn, but now let's total up all of our valence electrons. Nitrogen is in group 5A, so that means it has 5 valence electrons. Okay. Alright, hydrogen is in group 1, so it has 1 valence electron, but we have 3 hydrogens, so that's going to give us 3 valence electrons from hydrogen. Now if we take 5 and our 3, and we add them together, we get 8 valence electrons for this compound. Okay? Let's do the same for water.
Mr. Sims, if you're in the building. Ms. Settles, Mr. Sims, if you're in the building,
have
please come out to the main office.
Hydrogen, once again, which we already saw that hydrogen only has 1 valence electron, but there are 2 hydrogens. So that means we have 2 valence electrons contributed from hydrogen. And then oxygen is in group 6, so it has 6 valence electrons to contribute to our molecule. And this also gives us a total of 8 valence electrons. All right, get to our CH2O over here. Carbon is in group 4 and has 4 electrons to contribute to our atom, or to our molecule. You're welcome. And we only have 1 carbon, but then we get to hydrogen, and we have 2 hydrogens times that 1 valence electron per hydrogen to give us 2 coming from our hydrogens. And oxygen has 6 valence electrons. So now if we add those up, we got 4 plus 2 plus 6, a total of 12 valence electrons. Okay, so we've totaled it up for our 3 compounds. And I just want to talk about this side note real quick. If the whole molecule has a charge on it, like you see here for this NO2 with a -1 charge, once we get our total number of valence electrons, we need to either add or take away electrons according to the charge. So if it's a -1 charge, like in this one, that means the whole molecule has 1 extra valence electron. So whatever your total number is, you would add 1 electron to that. So say for this you have, let's see, 12, 17. Now you're going to have a total of 18 valence electrons for NO2 because it has that -1 charge, which means it has an extra electron in its total valence electrons. Now if we have one that has a +1 charge, that means that the whole thing has lost an electron. Okay, so in this case, whatever would be our total number of valence electrons, so 5 plus 4, that would be 9. 9 minus 1 electron because it lost 1. 1 less electron. So this means we're going to have 8 valence electrons for NH4. Okay. All right, that's just our side note. Now let's go back to our neutral molecules we're looking at. Okay, so we got 8, 8, and 12. All right, so now every time we've made a single bond, so remember we have our skeleton structures. I'll put them back, and this was 8 valence electrons. All right, then H2O, it looks like this for our skeleton, and we had 8 valence electrons. And CH2O looks like this, and we had a total of 12 valence electrons. Okay, so now we're going to deduct or subtract 2 valence electrons for each single bond that we already wrote in step 1. Okay? All right. So let's see. We have this structure. It has 1, 2, 3 single bonds. So 2 valence electrons per single bond. That's 3 times 2. 6 electrons we're subtracting. So 8 minus 6 leaves us with 2 valence electrons. Okay? All right. Now let's do that for this one. We've got 1, 2. 2 times 2 gives us 4. Because there's, let me just explain why. Every covalent bond has 2 electrons in it. So if we put 2 covalent bonds here, we've already used up 4 of our electrons because there are 2 electrons here and 2 electrons here. So out of our total 8 we could work with, now we're subtracting those 4 we used to make those bonds, so we've got 4 left. Okay, we come over to this one. We had 12 electrons, and now we've already made 3 bonds, so 3 times 2 electrons per bond gives us 6. So we subtract 6 from our total 12, and we have 6 remaining. Okay. All right. Now, the next step tells us to distribute the remaining electrons as unshared pairs so as to give each atom 8 electrons if possible. Now, an exception to that is hydrogen. Hydrogen only can fill up the first energy level, which only holds 2 electrons, so it cannot go up to 8 electrons. So when hydrogen has 1 bond to it, that one bond has 2 electrons in it, and hydrogen is happy with just those 2 electrons and can't take any more, really. All right, but nitrogen, like in NH3, is in the second energy level and can hold a total of 8 valence electrons. And right now it has 1, 2, 3 bonds around it, so that's 6 electrons surrounding our nitrogen right now because it's 2 per bond. So we only need 2 more electrons for nitrogen in order for him to get up to 8. Now, we have to look and make sure we have 2 left, which we do indeed have 2 electrons left to give to our nitrogen. So when it says distribute the remaining electrons as unshared pairs, what that means is to put 2 dots on nitrogen so that now he has 2, 4, 6, 8 electrons around him, and he has satisfied his octet. All right. So then we've used up the last 2 electrons and our structure is good. When we move up to water here, we have 4 remaining electrons. And we know hydrogen's already happy because it already has 1 bond, but our oxygen needs some more electrons.
E-Money Williams. E-Money Williams. Please report to the main office. You're
right now, oxygen has 4 electrons around it because of those 2 bonds. So it's going to need 4 more electrons to get up to 8. So we have 4 electrons that we can give to it. So if we use those 4 as lone pairs, so there's 2 of those, 3, 4 of our electrons, and we've used up the last 4. And now oxygen has 2, 4, 6, 8 around it, and oxygen is happy with its octet. All right, finally, we're going to move up to CH2O. In this molecule, we have used 6 already to make our single bonds, and our hydrogens are happy, but now we have to check out carbon and oxygen. All right, carbon has 2 to 4, 6 electrons around it, so carbon only needs 2 more electrons. But what about oxygen? Oxygen only has 2 electrons by it, and it needs 6 more to get up to 8. So 6 plus 2 would mean we need 8 electrons, but we only have 6 electrons left. So we can't just give carbon 2 electrons and oxygen 6 electrons because we only have 6 electrons left to give at all. So we're going to have to look at the last possible step. So let's move up to step 5. If there are too few, meaning not enough electrons, we're going to have to introduce multiple bonds. So this is double bonds or triple bonds. Okay, so if we're short by 2 electrons, we're going to need to introduce a double bond, but if we're short by 4 electrons, then you would need a triple bond. Okay, so we've already got, I'm going to draw it again, our skeleton structure where we've used 6 electrons, and we know carbon needs 2, oxygen needs 6. We've only got 6 electrons left. Okay, so if we need a total of 8 electrons and we only have 6, that means we're short by 2 electrons. Okay, so that means we're going to need a double bond. And the double bond, most logically, should go between our 2 atoms that really need more electrons. So now if we look at carbon, now carbon has 2, 4, 6, 8. We can get rid of its needs 2 because now it has the last 2. It has 8 electrons around it, so its octet is satisfied. Now we've used up 2 electrons in that double bond.
Students, if you're looking for the tag ed meeting, it's in Miss Max computer lab upstairs on D5.
All right.
So if you're looking for the tag
so we have 4 left. And oxygen now does not need 6 because now oxygen has 2, 4 next to it. So it only needs 4 more to get up to 8. And now we have enough because we have 4 electrons. So we can put 4 dots in our 2 lone pairs of electrons for oxygen. So oxygen now has 2, 4, 6, and 8. And get rid of that because now oxygen is satisfied. So let's look and try this with nitrogen. In the next video, we'll look at nitrogen.